Welcome to the final lecture in Unit 7. This is Zoltar Speaks, and it says the best way to predict the future is to create it. And so what we're going to do here is we've already talked about chemical reactions, balancing chemical reactions. We talked about the types of reactions, and so this is about predicting reactions. So what we'll do is we'll try to predict the products of the 5 basic types of reactions. We'll use the activity series to predict if single replacement reaction, meaning those oxidation reduction reactions, will actually occur, and we'll predict the products of double replacement reactions based on the solubility rules. So essentially what we're doing is we are predicting the 5 basic types of what products are, and then we're going to see, do all single replacement reactions happen, and do all double replacement reactions happen. So jumping into this, what we already know. Compounds and elements can combine, decompose, combust, and rearrange according to the different types of reactions. And so those different types we talked about were single replacement, double replacement, synthesis, decomposition, and combustion. And so we know that they can react according to those ways. We also talked a little bit about oxidation reduction reactions and precipitate reactions and neutralization reactions, and said that those are usually more broader terms that can encompass all chemical reactions. But normally what we do in this class is we stick to those 5 basic types. The single replacement, double replacement, combustion, synthesis, and decomp. Those are the 5 basic types we stick with. Now what we should have gotten out of the lab is that combining 2 reactions will not always produce a chemical reaction. So just because on a piece of paper we can put 2 reactants together doesn't mean that it'll actually happen when we go to the lab. And we also learned that not all metals will produce a chemical reaction. So when in a single replacement, when we put those guys together, they don't always react. That metal doesn't always react with the solution, and so we need to know when things are going to react and when they're not going to react. So how do we start? Where do we start? The main thing, reactants. We always start with our reactants and looking at our reactants to see if something's going to actually take place. The reactants of a chemical reaction limit what type of reaction can occur. So essentially, when we're really looking at this, we did look at the types of reactions and we looked at the reactions and products, but we can just look at the reactants and we can determine if a chemical reaction will take place. So in predicting products, when we talk about this, we're going to talk about it in terms of elements and compounds, kind of like what we did with the types of reactions. So starting here, if we start with an element and an element, we're going to have, we're going to have a synthesis reaction will occur, and it produces one single product. So an element plus an element is going to produce a compound. So it's going to produce a compound. It'll be a compound of the 2 elements that we started with. Okay, that's for a synthesis reaction. Now, a decomposition reaction, we're just starting with a compound. We start with a single compound. That means that we're going to have a decomposition reaction, and it will produce 2 products. And in general, it's going to be the 2 elements that we have. So we're going to deal with essentially a decomp where it just goes to 2 elements. Now you do have decomposition reactions where you go from a compound and it produces 2 individual compounds, but for this class what we're going to stick with is we're going to stick, if we start with a compound, it's going to break up into an element plus another element, and we'll stick with that for right now. If we start with an element and a compound, well, that means that we're going to have a single replacement reaction, and it will produce another element. It'll be the element that's in the compound plus a new compound. So an element plus a compound will produce an element plus another compound. And then a double replacement reaction, we start with a compound and a compound, and it produces a compound plus a compound. And that's just that double replacement where they switch partners, and it'll produce those 2 compounds. And then when we're talking about combustion reaction, if we have some type of molecule here plus oxygen gas, we're going to have a combustion reaction. Combustion reaction produces carbon dioxide and water vapor and energy. It produces carbon dioxide if that molecule is a hydrocarbon, and a hydrocarbon means that it's carbon and hydrogen, some form of carbon and hydrogen. So to have carbon dioxide, you have to have carbon in that molecule. Okay, if you don't have carbon in that molecule, you can't produce carbon dioxide. But generally, in a combustion reaction, you're always going to produce water vapor and energy, and you only produce carbon dioxide if that molecule has a carbon in it. So when we're predicting products, we follow the rules for that type of reaction. So in a synthesis reaction, we know that it's an element plus an element produces a compound. And so we follow the rules for that. In making a compound, you have to do crisscross if it's ionic. And we have to follow those types of rules. Now, all compounds must have a neutral charge, meaning we're not going to produce a polyatomic ion. And remember, write the formulas and check for diatomic. So when we're writing the formulas, that's crisscrossing. Make sure that we write the formulas correctly. Make sure that we're checking for diatomics as we do this. So let's look at our first example. So in our first example, it says speculate on what products will be produced when pure sodium is placed in pure water. So when we're looking at this, we're trying to put pure sodium in pure water. When we think about this, pure sodium is just Na. Okay, and it's pure sodium, and it has pure water, which water is H2O. Now, when we look at water, we see H2O, but one way that you can look at it is you can kind of think of water as a hydrogen bonded to a hydroxide. And usually that helps, especially when we start talking about acids and bases later on. Think of water as hydrogen bonded to a hydroxide. And so when we look at this, we have an element plus a compound. Well, an element plus a compound means we're going to have a single replacement reaction. So that means that this sodium is going to come in and bump off that hydrogen. So what is it going to produce? Well, sodium hydroxide. So we have to crisscross this. Na, which is +1, OH, which is -1, crisscross, and we get sodium hydroxide, which is NaOH, plus, now we bumped off this hydrogen, it'll be hydrogen by itself. Now remember, we got to check for diatomics. Hydrogen is a diatomic, it's part of Brinkelhoff, so we put a 2 there. And so possible products that could be made, we could have our sodium hydroxide and hydrogen gas. Those are 2 possible products that you could have in that type of reaction. Looking at our next one, it says predict the possible products of the following chemical reaction. So we have potassium iodide and fluorine. Potassium iodide and fluorine. When we're looking at this, we could go ahead and write their chemical formula. So potassium iodide is K and O. Potassium is going to have a +1 oxidation number, oxygen -2. So when we write this, it's K2O plus fluorine. And remember, fluorine's a part of Brinkelhoff, so we put a 2. Well, when we're looking at this, the one thing that we'll point out here, in single replacement reactions, so far, the element that's been by itself has been a metal. And in this case, it's a nonmetal. And so this nonmetal is going to try to replace that nonmetal. So when we're looking at it, nonmetals replace nonmetals, metals replace metals. So that fluorine is going to try to bump off that oxygen and create potassium fluoride, which is KF. We crisscross potassium fluoride, and then oxygen will be by itself, and it's also a diatomic. Remember, this is an element plus compound, single replacement reaction, because it's an element plus a compound. So some possible, we're going to have potassium fluoride, oxygen gas. We could have those in that type of reaction. And let's look at this one. It says predict the possible products of the following chemical reaction. So here we have an element plus an element. Magnesium is Mg plus oxygen, which is diatomic, it's O2, produces magnesium oxide. And we've seen this one before. Mg, which is going to be +2, oxygen -2. Since they're the same, what can we do? Reduce it down to a 1 and 1, crisscross, and we get MgO. Okay, element plus an element produces a single compound, which we have here. Now, jumping into the activity series. Now, what the activity series is. The activity series is a list of metals, and this is a key here, it's metals with increasing reactivity. The most reactive is on the top, so the most reactive metal is going to be lithium. and the least reactive is on the bottom. So the least reactive thing we have here is gold, and that is going to be our activity series. Now, we can look at it and we see that lithium is unstable by itself, so it will replace anything below it. So lithium, if it comes across, and we use the activity, and this is a key thing here that I would write down, we use the activity series when we're talking about single replacement reactions. Single replacement reactions. And so lithium, if it's by itself, doesn't want to be by itself. It's very unstable, so therefore it'll replace any compound that has any metal, any of these guys, because lithium is so reactive. That's what the activity series is. It tells us if single replacement reactions are going to take place. So it's for single replacement reactions only, and it's for, this is a list of metals. Now, the activity series of anions, so non-metals, is just your halogens on the periodic table. So if you look at your halogens on the periodic table, that's group 17. That's what it is. That's the activity series of anions. So fluorine's the most reactive, and then chlorine, bromine, iodine. Works the same way. We just don't need an activity series because we have the periodic table and it works out that way for us. So, but it works the same way. If it's on top, it'll replace anything below it. So if a pure element is higher on the series, it will replace the cation or anion in that compound. And the key thing here, if the single element is lower, so iron is a single element and it's trying to replace that magnesium in magnesium oxide, the reaction can't happen. Okay, so since iron is below magnesium, it cannot replace any magnesium that's already in a compound. Okay, it has to be on top for it to actually happen. So single replacement only has to be on top for the reaction to occur. Let's jump into an example. It says predict the product, if any, and that's the key thing here, if any, for the reaction below. So when we're looking at this, we look at what's by itself. This is barium, and we find barium on the periodic table, or not the periodic table, but the activity series. It's right there. There's barium. Now, the only thing that barium cannot replace is it cannot replace lithium and it cannot replace potassium. So we look at what we're dealing with. We're dealing with an iron 3 nitrate. So we're trying to figure out, can barium replace iron? Well, we look, is iron below barium? Well, yes, it is. It's right there. So this reaction can take place. Since it's a single replacement reaction, barium is going to replace that iron. So iron will be by itself, and then we'll crisscross barium and nitrate. So barium is Ba. It has an oxidation number of +2. Nitrate is NO3, -1 charge. We go ahead, crisscross these guys, and we get Ba NO3 2. And then what we would do from here is we would go ahead and we would balance the equation, because remember, we have to have balanced equations to work with, but right now we're just predicting the products. So this reaction does take place and it produces iron and barium nitrate. Our next example, it says predict the products, if any, for the reactions below. So we have magnesium and calcium carbonate. So magnesium is just Mg plus calcium carbonate. Well, calcium is Ca. It has an oxidation number of +2. Carbonate is CO3 with a -2 charge. And since we know that it's a 2 and a 2, what can they do? They can be reduced. So we reduce these guys down to 1 and 1 and crisscross them, and we get CaCO3. We really didn't need to do that to figure out if the reaction takes place, but it's good practice. So now we look at it. What's by itself? Well, let's pick another color. Magnesium is by itself. Find magnesium on the activity series. It's right there. So, and then we have our other one that we have calcium. So we find calcium on the periodic table. It's right here. Now, remember, magnesium can replace anything below it. Is calcium below magnesium? No. So this reaction will not take place because calcium is not below magnesium. It's actually above it. So this would be no reaction. Now, next one, it says predict the products, if any, for the reaction of barium and zinc nitrate. So we have barium, and it's going to try to replace, that zinc. So we find barium, barium's right here. We find zinc, zinc is right there. Is zinc below barium? Why, yes it is. So this reaction will take place. So we have barium, which is Ba, plus zinc nitrate, which is Zn, and zinc is going to have a +2 oxidation number, NO3, -1. So we have ZnNO3 2. So our products for this, zinc will be by itself, and then what we will have is barium bonded to the nitrate. So we have to crisscross again, barium +2, nitrate, NO3 -1, and our other product is barium nitrate. And those would be our products of that reaction. Now, when we talk about double replacement reactions, we really have to talk about solubility and what solubility really means. Solubility is just a substance becomes dissolved in another. Ionic substances will dissolve or disassociate. The key thing we have here for when ionic compounds get dissolved is called dissociation. So they dissociate in water. They become dissolved in water. And we should know this just by putting in salt in water. We see that salt will dissolve in water. It dissociates in water. That's what solubility is. So something is soluble if the compound stays in the aqueous form. Aqueous means dissolved in water. It's insoluble if it precipitates into a solid and falls out of solution. We call insoluble things precipitates. They form a solid at the bottom. You can kind of see them fall out of solution. You usually see a color change with that, or you just see the solid form at the bottom. But soluble means it stays in the aqueous form. Insoluble means that it produces a solid. So to do this, not when everything reacts and everything else, not all things will dissolve. So what we have to do is we have to look at the solubility rules. Now the solubility rules determine what is soluble and what is insoluble. So in this case, when we look at lithium phosphate, we look over here and we can see that phosphate is right here, since lithium is bonded to it. And that means that it's in the insoluble list. So it's not soluble, it doesn't dissolve. Now there are some exceptions. If that phosphate is bonded to an ammonium, that cation, it will be an exception. So if you're an exception to being insoluble, you become soluble. And if it's bonded to an alkaline metal, cation, then it's an exception. And so when we look at this, we see that it's an exception, so therefore it's an exception, it's soluble. But when we look at calcium phosphate, well, we know that phosphate is insoluble unless it has an exception. It's bonded to our ammonium or an alkaline metal. Well, calcium is not an alkaline metal, it's an alkaline earth metal. So therefore, since it's bonded to phosphate, it's insoluble. It will not dissolve in solution. It will not become aqueous. So it'll stay in its solid form even when you put it in water. So, solubility rules. What we use them for is it predicts if a double replacement reaction will occur. So no precipitate, no reaction. So if we do not have something that is insoluble, guess what? No reaction is taking place. Now, all ions are still in their dissociated form. That means that if everything is still dissolved, there's no precipitate, we have no reaction. So precipitate means that a double replacement reaction has occurred. Now, a cation and anion precipitate out of solution. That's what it means. Precipitate equals double replacement reaction. We have to have a precipitate, and this is the classic example of it. We're putting two clear liquids together, and we produce that solid, that yellow solid. So let's jump into some examples to kind of get this. It says predict if a precipitate would form from the following reaction. So we have magnesium, nitrate, potassium perchlorate. So when we're looking at this, what we look at is it's a double replacement reaction. So these guys are going to switch partners. So magnesium is now going to be bonded to perchlorate, which we have to do the crisscross, Mg, which is +2, ClO4 -1, and so we'll get MgClO4 2 plus potassium bonded to nitrate, which potassium has a +1 oxidation number, nitrate has a -1, so it's KNO3. So when we're looking at this, we look and we see, will one of these guys over here, one of our products, be insoluble? So when we're looking at this, we look perchlorate. We find perchlorate, it's right there. It's in the soluble list. There's no exceptions to it. So guess what? Magnesium perchlorate, soluble. That's aqueous. And then we have potassium nitrate. So when we're looking at this, we find nitrate. It's right here. It's in the soluble list. And there's no exceptions. So guess what? That's aqueous as well. So if we have two aqueous substances, no solid, guess what? No reaction. Okay, let's jump into our next one. It says predict if a precipitate will form from the following reaction. So we're going to have calcium, and it's going to switch partners and now be bonded to chloride. And then we're going to have ammonium bonded to carbonate. So let's see if potassium chloride will make a precipitate. So when we're looking at this, we find the chloride. There it is. And let's switch. Here we go. There's the chlorine. Does it have any exceptions? So if chlorine is bonded, it's in the soluble list, but if it's bonded to silver, or if it's bonded to lead 2, or if it's bonded to mercury 2, it's not. So guess what? Our calcium chloride is going to be aqueous. Then we look at this and we have ammonium bonded to carbonate. So when we look at this, we have carbonate right here. It's in the insoluble list, but when you look at the exceptions, compounds of ammonium carbonate will be an exception to being insoluble, so therefore this is soluble as well. It's aqueous as well. And so therefore that reaction, no reaction has occurred because there's no precipitate. And let's look at our last one. It says predict if a reaction between silver nitrate, so we have silver nitrate, and zinc chloride. So we have silver will bond to the chlorine, and then what we'll have is we'll have the zinc switch partners and bond with the nitrate. So when we're looking at this, we look to see if a reaction has occurred. So silver bond to chlorine, we find chlorine, there it is. It's in the soluble list, but let's look at its exceptions. A compound of silver, and it's silver chloride. So guess what? That means that it's an exception to being soluble, so therefore now it's insoluble. So silver chloride will be a solid, and we check out, will zinc nitrate be a solid? Here's nitrate. Does it have any exceptions? No. So guess what? This reaction has occurred, and it will produce that silver chloride as a solid, and that zinc nitrate will be left in solution. That will still be aqueous.